Welcome everyone, I'm Norman Wildberger. This is a series on elementary mathematics from the years K through 6, aimed primarily at teachers and parents of younger children, or in fact anybody wishing to solidify their understanding of very foundational elementary aspects of mathematics. This is New Year's Day in 2013, and so I'd also like to take the opportunity of thanking my viewers and subscribers for their attention and their many nice comments and remarks that I've gotten over the last year. So I may not always respond to a note of or a comment, but I read all of my comments and I do appreciate all of your input. So today we're going to talk about some applications of basic multiplication. We're going to look at some area problems associated with two-dimensional figures and how to apply multiplication to calculating areas in a simpler way than just counting square by square. So here's a good place to start off. This is the 10 by 10 square, which of course makes a total of 100 because we know that 10 times 10 is 100. So there's a row of 10 here, another row of 10, and altogether we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rows of 10. So this is a good thing for young people to see so that they get a sense of how much 100 actually means. So there are exactly 100 little cells in this big square. And it might be a little bit easier to see or to understand if we draw these guidelines here so that this is 5 and this is 5. So we've subdivided with these two lines into 4 smaller squares, which are each 5 by 5. So there's altogether 25 there, 25, another 25, and another 25, making the total of 100. Okay, so in this region we can of course look at all kinds of smaller rectangles. For example, we can look at this red one. Okay, so this red one here is a rectangle which has 1, 2, 3, 4, 5, 6, 7 rows and 1, 2, 3 columns. It's a 7 by 3 rectangle. And so we know its area is 21 because 7 times 3 is 21. On this blue rectangle here, this is a 2 by 4 rectangle, and 2 times 4 is 8. So there's altogether 8 squares in that one. So if we wanted to calculate the total area of the shaded area, this L-shaped region formed by the blue and the red rectangles, that whole region there, well then that area is going to be the sum of the area of the red rectangle and the blue rectangle. So the shaded area is altogether 7 times 3 plus 2 times 4. We have to add the two areas to get the total area. 7 times 3 we've said is 21. 2 times 4 is 8. So we have to add 21 plus 8. How do we do that? Well, remember that 21 really means 2 tens and 1 1, and 8 means 8 ones. So we add by adding the ones. 1, 1, and 8 ones makes a total of 9 ones. And we still have 2 tens left over from the 2 tens in 21. So we get 29. Another way of thinking about it that young people will often do is they say, well, let's start with 21 and add 8. So if we add 1, well, that'll make 22, 23, 24, 25, 26, 27, 28, 29. So we've added 8 onto the 21 we started with. We've ended up with 29. We counted from 21 to 29, one step at a time, altogether 8 steps. So this kind of problem where we find an area of a composite figure that rests, of course, on this basic principle that multiplication corresponds to the area of a rectangle. This is a useful kind of problem to improve young people's skills at multiplication and at elementary addition. And it reinforces this very crucial idea that multiplication should be visually thought of as finding an area of a rectangle. That's what it corresponds to fundamentally. That's how we define multiplication to begin with. Right? So we want students to make sure that they understand this important connection between multiplication and the area of a rectangle. This might be a good place to make a short historical note. It's not bad for young students to get a little bit of exposure to the history of mathematics, to realize that mathematics is an ongoing process that's been going on for a long time. It's been developed over a long period of time by people in different cultures. And one of the very most important contributors to mathematics were the ancient Greeks, by which we mean rather loosely the Greek culture around the Mediterranean region, which included not just Greece but also Italy and Turkey and parts of Africa, in particular Alexandria. So that whole area and that time, roughly a 1,000-year period from say 700 before Christ to say 300 after Christ. That's the Greek period of mathematics. And there were many notable Greek mathematicians, including well-known names Pythagoras, Euclid, Archimedes, Apollonius, Aristotle, Eudoxus, and in fact many more. And the connection here is that the ancient Greeks thought of numbers rather geometrically, much more geometrically than we do today. So they preferred to think of numbers or quantities as physical extents, perhaps of line segments or perhaps of rectangles. So a number was to them primarily a line segment. So for example, this line segment represented the number 3, 1, 2, 3, while this line segment might have represented the number 4, 1, 2, 3, 4. But in fact, they didn't actually need to subdivide the line segments. They just thought of this line segment as being some quantity and this line segment as being some quantity. And so then multiplying these line segments, for them, that amounted to the geometrical construction of creating a rectangle whose two sides were the same as the two sides that we're multiplying. So this would be what we call a 3 by 4 rectangle. To them, this is the product of this line segment with this line segment. So this idea of multiplication as forming a rectangle goes back a long, long time in history. So it's probably a pretty good idea. That's why I emphasize this important way of thinking for young people. So let's have a look now at some area problems involving multiplication. So what we're trying to do is we've got some figure like this and we're going to find the area of this figure. Of course, there's one very simple way of doing it, which is just to count the number of squares involved. So we could go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. All right, but we want a somewhat more sophisticated way of doing that, which works even if the rectangles were much bigger, where counting might be a very laborious process. So the idea is, well, we know that areas of rectangles are relatively simple to find. They're basically multiplications. So we want to connect this with areas of rectangles. Well, this itself is not a rectangle, of course. So we have to do something a little bit more sophisticated. And what we're going to do is we're going to break it up. Okay? We're going to break it up rather arbitrarily, perhaps, by making a cut along here. And then that cut separates it into this rectangle here and this rectangle here, which is actually just a square. All right, so let's have a look at this rectangle here. Maybe I'll shade it. All right, so I'm just talking about that rectangle there. What's its area? Well, its dimensions are 1, 2, 3, 4, 5, and 1, 2, 3. So this is a 5 by 3 rectangle. And so its area is going to be 5 times 3. And hopefully we know what 5 times 3 is automatically because we've memorized the multiplication table. We know that that's equal to 15. And what about this little area here, this smaller rectangle or square? Well, its dimensions are 2 and 2. This is a 2 by 2 square. And we know that 2 times 2 is equal to 4. So we can put this together. Maybe I'll shade that one the other direction. Okay. So we could put this together by saying that the total area equals, well, let's write it down in terms of these things. It's 5 times 3, it's the area of this one, plus 2 times 2. That makes it clear what we're doing. We're adding the area of this thing to the area of this thing. Okay, and what is 5 times 3? We've seen that that's equal to 15, and 2 times 2 is 4, so we have to add 15 and 4. How do we do that? Well, we can just add 5 and 4. 5 and 4 is 9. So the total number of ones here is 9, and there's still 1 10 left over, so that's going to be 19. And another way of thinking about that, a more elementary way, is to start with 15 and then add 4. So if we add 1, we get 16, add 2, we get 17, add 3, we get 18, and we add 4, we get 19. So either way, we get a total of 19, which of course agrees with our original count. I might just mention that there's another way of doing this. So an alternative way would be to divide this rectangle into 2 different rectangles by, say, making an initial cut in this direction. So if we did that, then we'd find that the total area is, well, the area of that top part would be 3 times 3. Let's put it in brackets. That's the area of that square there. And then the area of this rectangle on the bottom would be, well, it's 2 by 1, 2, 3, 4, 5. That's a 2 by 5 rectangle. And that's equal to 3 times 3 is 9. 2 times 5 is 10. Altogether we get 19 as before. So we get the same answer, independent of which way we cut the original figure into these simpler, more fundamental rectangles whose areas we can compute just by doing a single multiplication. So we're employing the power of the multiplication table that we've learned to very quickly calculate areas of rectangles and then put them together. All right, so let's have a look at some more examples of this basic idea. So here's a slightly bigger figure, and we want to find its area. So we need to cut it into some rectangles. And I hope you can see that there's 2 ways of doing that. We could cut this way, or we could cut this way. Okay, let's choose to cut this way. All right, so then we could say that the area equals, the area of this one is 1, 2, 3, 4, 5, 6 times 1, 2, 3, 4. So that's a 6 by 4 rectangle here on the left. And this one here is a 1, 2, 3 by 1, 2, 3, 4, 5. So it's a 3 by 5 rectangle. Okay, what is that? 6 times 4 is 24. 3 times 5 is 15. How are we going to add 24 to 15? Well, we should think about adding the 1s and adding the 10s. If we add the 1s separately, there's 4 1s here and 5 1s there. Add them together, we get a total of 9 1s. There's 2 10s here in the 24, and there's 1 10 in the 15. So if we add the 10s, we get 3 10s altogether. So we get 3 10s and 9 1s for a total of 39. And I'll let you check that if you cut it in the other way, you'd get a different computation, but the answer would still be 39. All right, how about this one here? We've got a rectangle with a sort of a piece sticking out of it. Well, I guess the simplest thing to do is just to cut that piece there and think about this as being the sum of this rectangle right here and then this smaller rectangle here. All right, so we'll write area equals, okay, how about the big rectangle first? 1, 2, 3, 4, 5, 6, 7, 8. It's 8 in that direction, and 1, 2, 3, 4, 5, 6 in that direction. So it's an 8 by 5 rectangle. No, 8 by 6. We said 8 by 6. And so its area is 8 times 6. What about, let's make that proper 6. And what about this one here? Well, that's a 2 by 3 rectangle. So we have to add 2 times 3. All right, what are these things? 8 times 6. That is 48. 2 times 3 is 6. When we add 48 and 6, what are we going to get? Well, here there's 8 1s and here there's 6 1s, and when we add them together, we get more than 10. We get, in fact, if we add 6 to 8, we get 9, 10, 11, 12, 13, 14. That's what you get when you add 8 and 6. So you get 14. And then we still have 4 10s left over. So how much is that altogether? Well, the 14 is 1 10 and 4 1s. We still have a 4 there representing 4 10s. So altogether we have 5 10s and 4 1s. Which we could also get by just thinking about starting with 48 and adding 6. 48 and then 49, 50, 51, 52, 53, 54. So the total area here is 54. Here are 2 somewhat more challenging problems. To find the areas of these 2 things. Maybe you'd like to have a go before I explain how to do it. All right, so this first one is a rectangle with a hole. There's a hole right here, like a window. And we're not going to include that in the area. So the area is just the stuff that's all the little boxes, not including this window. So if I was going to shade it, I could shade it like this. All right, so that's the region that we're trying to find the area of. Okay, so, well, there's different ways of doing this. We could subdivide this into a bunch of rectangles and then try to add them all up. But perhaps a more conceptually simple way is to find the area of the big rectangle, including the window, and then subtract the area of the window. Remove the area of the window from the total area of the big rectangle. So let's write down an equation for that. And I'll write it like this. Area equals, all right, what's the area of the big rectangle? Well, let's see, it's got 1, 2, 3, 4, 5, 6, 7, 8 rows. And it's got 1, 2, 3, 4, 5, 6 columns. So it's an 8 by 6 rectangle. And now we should subtract the area of what's inside. We need to take away. How much are we taking away? Well, we have to sort of imagine this inside here. We haven't actually filled it out, but if we were going to, let me just sort of put dots along here so we can see that this is actually a rectangle here as well. This is a 3 by 2 rectangle. So this is a lot like the previous question. Instead of having 48 plus 6, we now have 48 minus 6. So 8 times 6 is 48, and 3 times 2 is 6. So now we have 48, and we have to subtract 6. So we haven't talked too much about subtraction yet, because it's a kind of secondary operation. Addition is more fundamental. But nevertheless, we should be able to do it in this simple case. So if we start off with 48 and we take away 6, what are we going to get? Well, let's just do it in a simple-minded way by taking away 1 at a time. So if we start with 48 and we take away 1, we're going to get 47. Take away another one, we get 46. Another one, 45. Another one, 44. Another one, 43. And then the sixth one, 42. In terms of tens and ones, there's 8 ones here, and we're subtracting 6 ones, so we end up with 2 ones. And we have the 4 tens here, and we're not subtracting any 10s, so we still have 4 tens left over. How about this problem here? Well, we can think about this as being subdivided in a number of ways. We could lop this little piece off here and then lop this piece off here and make 3 rectangles. Or another way would be to use just one cut. That's probably more efficient. So if we cut along there, then we see that we get 2 rectangles. So in this case, the area equals the area of the top rectangle is 3 times 1, 2, 3, 4, 5, 6, 7. So it's 3 times 7. Put brackets around it. And then that bottom rectangle is just a strip with 1, 2, 3, 4, 5, 6, 7. Also 7 squares. So we have to add 7. Well, what's 3 times 7? It's 21. And if we add 7 to that, we're going to get 28. And now that we think about it, we can see that, well, there might have actually been a simpler way of doing this. Another way of tackling this would have been to say, well, suppose that we cut rather this little rectangle off here, and we move it over right there. So if we take that rectangle and move it over there, then we get, as a result, a complete rectangle. So then we would also get, another way of doing it would be that the area is the same as the area of this big rectangle that we get by moving this. That's a 4 by 7 rectangle. And 4 times 7 is also 28. So those are a few examples of different ways of cutting things up and reducing area computations to the areas of rectangles, which is multiplication. That's our multiplication table that we've memorized, haven't we? So the simple lessons that we've learned today is that when we're trying to find the area of a complicated figure, we should try to split it up into simpler parts, typically rectangles. Secondly, we should use multiplication to find the areas of rectangles. Let's try to get our students to immediately think about multiplication when they see a rectangle, not to count row by row by row, but rather to count how many rows there are, how many columns there are, and then to use the multiplication table. And then finally, we have to add areas of parts to get the area of the whole. If we've cut things up into parts and calculated areas individually, then putting that together is addition. And the basic principle that we've seen a number of times is that it shouldn't matter how you split up the initial figure, because ultimately you're counting how many little cells there are in the whole figure, and that number is independent of how you cut things up. So there can very well be different ways of arriving at the final answer. And sometimes it's instructive to try different ways on the same problem. It's good practice for arithmetic, and also to make sure that we've got the right answer. It's a check. If you get the same answer doing it two different ways, you have more confidence that you've done it right. Now let's have a look at a few practice problems that you can try yourself. So here are 4 examples of figures that I want you to calculate the areas of. And I want you to do that using the methods that we've talked about today in terms of finding rectangles and either adding rectangles or in some case perhaps subtracting rectangles. Note that in this example here there's a little window here as well as a chunk removed from the side here. Alright, so just some practice problems for you to practice applying multiplication to finding areas. Next time we're going to think about applying our increasing understanding about numbers to different aspects of real life. And we're going to start by looking at the time scale of a human life, a century roughly, and we're going to look at how the mathematics of the numbers from 1 to 100 relates to various phases of everyday life. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening, and Happy New Year.